In this video, we're going to start our discussion with matrices. So a matrix is a rectangular array of numbers within brackets. Okay? So this is an example of an m by n matrix, meaning that it has m rows and n columns. Okay? So the order or dimensions of a matrix is the number of rows by the number of columns. So we've written a couple of examples below and the actual dimensions. For instance, the left matrix has 2 rows going across and 3 columns going up and down. So that is a 2 by 3 matrix. All right, so let's talk about some other terminology then. A square matrix is a matrix that has the same number of rows and columns. So for instance, that matrix 1, 2, 3, 4 is a 2 by 2 matrix. 2 rows, 2 columns, the same number. A column matrix is a matrix with 1 column. So the 911 matrix is 3 rows going across and 1 column going up and down. So the dimensions here is 3 by 1. And a row matrix is a matrix with 1 row. So the 516 is a 1 by 3 matrix. Now, matrices can represent a system of linear equations. These matrices are what are called augmented matrices. So for the example on the left, notice the first row, 3, negative 2, 5. Notice 3x, negative 2y equal to 5. That vertical bar, think of it as like an equal sign. The second row, 5, 3, negative 2, 5, 3, and negative 2. And again, the bar, think of it as an equal sign. All right, so let's fill in the augmented matrix to the matrix on the right here. So x plus z is equal to 2. 1x, 0y, 1z, 2. 3x, 4y, negative 1z, negative 6, and 0x, 1y, negative 5z, and 0. So there's my augmented matrix for this. All right, so row operations. These are operations used to solve a system of linear equations when written as an augmented matrix. So there are 3 that we will talk about. Interchanging 2 rows, multiplying a row by a constant, or multiplying a row by a constant and then adding it to another row. All right, so let's take a look at each of these row operations then. For the first matrix, all I'm doing is switching row 1, row 2. So easy to do. There's my new row 1 and my new row 2. That's interchanging 2 rows. Now, for the next one, what is that telling me? I'm going to take every single element or object in row 1 and multiply it by 1/5. So 1/5 times 5 is 1. 1/5 times 6 is 6/5. No decimals, always fractions. 7 times 1/5 is 7/5. And 1/5 times 1 is 1/5. Notice I'm not doing anything to row 2, so I rewrite it exactly the same. There's my new matrix. All right, so now I'm doing 2 different row operations for this. Okay, let's start with the negative 4r1 plus r2 is my new row 2. So what am I doing? I'm going to take negative 4, multiply by 1, and add it to 4. And that's 0. Now I'm going to take negative 4, multiply by 2, and add it to 5, and get negative 3. I'm now going to take negative 4, multiply by negative 3, and add it to 6, and get 18. And then on the other side, negative 4 times 1 plus 1 is negative 3. So those are now going to be my new elements in row 2. Now, row 3 is a little bit more simple. All I'm going to do is take r1 plus r3, and that's my new row 3. So what? I'm going to take 1 plus 0. I'm going to take 2 plus 3. Negative 3 plus 4. I'll take 1 plus 2. So those are going to be my new elements in row 3. So now row 1 did not change. row 2 now, and then row 3. There's my new matrix. Okay, so now then, we can talk about solving systems of linear equations using augmented matrices with two different procedures. One is what's called Gaussian elimination with back substitution, and the matrix is in the form of row echelon form, or what is called REF. Or you can use Gauss-Jordan elimination, and the matrix then is in row reduced echelon form, or RREF. Well, let's talk about row echelon form first. So that's any rows consisting entirely of zeros are to be put at the bottom of the matrix. For each row that doesn't consist entirely of zeros, the leftmost non-zero entry is 1. And for two successive non-zeros, the leading one in the higher row is farther to the left than the leading one in the lower row. So below, I've shown 3 different examples of REF form. Again, notice the ones, if possible, start on the top left and move diagonally down. For the third example, though, that's hard to do because we have a row of zeros, and that's fine. All right. So now let's take a look at the 2 examples on why they are not an REF form. For the left one, notice the ones do not start at the top left and move diagonally down. But if I interchange row 2 and row 3, that is an REF form. Now, why is the second example there not an REF form? Well, take a look at the second row. The first non-zero entry is not a 1. In this case, it's a 5. Simple solution, multiply the second row by 1/5, and now you'd be an REF form. All right, so now let's talk about solving systems of equations using Gaussian elimination with back substitution. First of all, we want to write the augmented matrix. We want to use row operations to rewrite the matrix in row echelon form, or REF. Write the matrix as a system of linear equations from step 2. Use the equations found in step 3 with back substitution to find the solution of the system. Before we even get to that, I want to talk about back substitution. Okay? So I want to solve the following systems using back substitution. Now, notice for this example, it is an REF. Okay? Now, let's write out the system of equations then. Notice, if I'm using x and y, the bottom equation is y equal to 5. I can easily substitute that in to solve for the top equation. Now, the solution to this is negative 17.5. All right, so I want to show one other example for this. Okay? Again, notice this matrix is in REF form. Again, we will assume the variables are x, y, and z. So let's write out. Now again, notice the bottom equation, z is equal to 3. I can back substitute into the second equation. Okay. Now, I can take this y equal to negative 7 and this z equal to 3 and solve for the top equation for x. Again, easy equation to solve for. Okay. So now write it as an ordered triplet. Remember, it's x, then y, then z.